right here. So good morning, Astronomy 1020. Welcome back to our first post-exam lecture. Today we'll be starting lecture 8 on chapter 15, which is about stars in general. We're going to do a homework today, homework number 7, which is questions from chapter 15. And we're also going to talk a little bit about the exam, because as we were discussing before the recording began, it was long and people hated it and they're mad at me. And I expect that. Okay, so let's see why it may not be as bad as you're thinking. Okay, let's try to understand. Now, you remember me and Austin. Austin, are you in the background? Are you a troll today or something? Or are you just not even here? Okay. Well, Austin and I had a little discussion where he wanted to know if there was a curve to the course. And I said, I'm going to discuss that after the exam. And he said, that's sus. Okay, so today we're going to get into talking about that curve so that you can understand how your grade is determined. By the way, how many of you that are sharing video with me, did you look at your midterm grade? Show me your hand if you did that. Okay, so you already got a sense of, okay, Gianna, you got a sense of what's going on. I want to take just about 5 minutes to explain exactly how your grade was determined. Okay. Okay, as you guys know, your grade is a mixture of 25% homework, 25% lab, 25% midterm, and 25% final, okay? So we have homework at 25%. It's all quarter weighting. Okay. Now, I want to imagine a typical student, like one of the students that I know by name and face who interact with me, who comes to all of the lectures and does all of the homework and all of the labs as I recommend, okay? If you just come and hang out with me, so I've got a little bit of glare here, guys. Hold on a second. Okay, I'm sorry about that. Oh, it's the blinds. Sorry, I was having lighting issues here. So listen, if you just come to class, hang out with me, and participate in the class, I make sure that you get your homework done right. I make sure that you get your lab done right. So as long as you just show up and hang out and participate, you don't even have to participate. You can be a troll, but you just kind of have to be here and be a part of the class. There's no reason you cannot get a 100% on your homework and a 100% on your lab, especially because I gave you guys the amnesty the week beforehand, which some people made use of, but not everyone. I was confused by that. Now, the midterm was hard and it was long, and it wasn't supposed to take your whole day. You were supposed to be trained and know how to do dimensional analysis and know what formulas to choose from. But obviously the real world doesn't work like that, and you haven't spent that many weeks learning this stuff, so you're going to be confused. Let's say you're a student who just did okay on the exam and you got a 50%, which is what well, I'm sorry, Christopher, those things tend to come together at one, but you made it through it. Let's say that you got a 50% on your exam, which most people don't think of doing 50 as being good on a test, all right? Riordan, you don't understand what's going on. Okay, so Riordan has a question. She actually had the pleasure of having an in-person class, with me. And for the day classes, which most of you are a part of, I only meet them for 1.5 hours twice a week. The night classes I meet for 3 hours once a week. The night class gets one big midterm and one big final, just like you guys do. The day class gets 2 midterms, each of which are 50 points. I decided, since I'm mixing day and night students together, that everyone would do 1 midterm and everyone would do 1 final. I like it that way because it's less assessment but more horribleness in one shot. So if that makes any sense. So let's say that you got a 50% on your midterm, which a normal person would not think of as being good on a test, but I think is a fair and respectable grade. I cannot compute your average. This is what I had to work with for your midterm grade. But I don't want to weight these at equal weighting because it'll give inflated weight to homeworks and labs. So I presumed that you would get the exact same score on your final exam that you did on your midterm. Now, that doesn't have to be true. That's up to you. But I presumed that your final exam score would be the same as your midterm score. Now, let's look at this typical student. 1 + 1 + 1 gives you 3. And if you divide it by 4, this student has a 75%. And this is where I apply my curve, a curve that I've developed over many years of doing this. And the curve goes, well, a little something like this. I peg, I don't want to get distracted by this here, so I'll do it over here. I peg B- to a 65%, all right? And I go in roughly 5-point increments from there. So a B would be 70% and above. A B plus is, 75% and above. A minus is anything over 80%, and A is anything over 85%, which is a pretty generous curve. On the lower end of the scale, a C plus is everything over 60. There is no C minus at CCRI. So that'll yeah, I do recognize this stuff is hard as hell. It's called astrophysics. It's not basket weaving 101. It's not, it's not Pottery Barn 207. It's astronomy. That's what you signed up for. C, I extend all the way down to, because think about it, all right, before you guys start jellyfishing, whatever the hell that means, listen, guys, it is a hard class, but I've gone out of my way to make it really effing easy for you by doing all your work with you and giving you lots and lots of attention if you need it, and then maybe punishing you twice during the semester. 1 midterm and 1 punishment for the final, and that's it, okay? The rest of it, I'm with you every step of the way. Okay, now, I extend C down to 50%. This is the real magic because this is what makes sure that you're going to do well if you just show up and hang out with me. 45% is a D plus. If you're below 40%, I consider that failing, which luckily, well, normally few people are, but this is a kind of terrifying semester for me because I normally have 14 students per class, and 2 weeks before the start of the semester, they doubled the class enrollment to 28 students. So I have hundreds of students this semester, and some of them, I don't even know who they are because they've never logged into a class once. So there are some people who failed because they just didn't do anything. And I feel bad about that, but I can't force them to come to class. Let's look at a hypothetical student who does all their homeworks, all their labs, and gets a 50% in the test. That student has a 75%, which is a B plus. Not bad for someone who got a 50 on an exam. That's pretty cool. So I hope you understand the moral of this story. The moral of this story is all you have to do is this is the midterm exam. Yes, that's what I'm trying to say. That was this student's midterm exam. It's okay, Gianna. Maybe I wasn't clear. The most important thing you can do in this class is just show up and follow the bouncing effing ball and turn in your homework and lab, and it's gonna be cool, whatever you get, all right? And if you can get a little bit higher on that final exam, okay, cool, Cameron. I like coming here too. I always have a good time. This isn't the worst job I've ever had, so I appreciate that. But do you guys understand? Do you feel like you have enough transparency? What is? I worked at a tie shop once, and I had to like sell people neckties and bolo ties, and I was a really, really bad employee. When no customers were in there, I would read books on astronomy, And the woman would come in and go, why are you reading books about aliens all the time? And I'd say, no, this is good stuff. This is really cool. And she's like, you're always reading about aliens. So that job didn't go well for me. Okay. Anyways, does this help make things more transparent and less sus for you guys? Do you have any questions about this? Okay. Yes, less sus. Okay. Can I make a recommendation? I'm not going to do another general amnesty for the homeworks before this because I'm just done with the first half of the semester. Now we are getting into my favorite topics in astronomy, and that's when I think the class gets good. Also, you guys have built up your muscles, so you're a little bit stronger than you were before, and that means we can have a more intelligent conversation about cool things in space. You'll be surprised, Stacy. Yes, and we're going to talk about black holes. That's what this is all going to culminate in. But for now, here's your strategy, guys. Just make sure you get the homework and lab done. And if, God forbid, you do get sick, well, you've got a week to watch that homework and that lab session and get it into me, all right? Obviously, if you pay attention in the lectures, when I'm punching stuff into the calculator, you guys need to do that too, okay? And most of the people that I can see here, I know you guys, and you do it. I don't know about the trolls in the background. I mean, you guys could just be taking a nap, but you need to be punching your numbers into this calculator, all right? And that goes for nighttime students who I don't interact with that often as well. Okay, so remember this scale, and remember, do all your labs and homeworks, and everything is going to be okay. All right, let's talk about stars. It seems like there are no other questions. So. And I know that test was long and hard. I designed it that way. Okay. Stacy? Oh.
Yeah, I was going to ask, so we should expect, just to plan, we should expect the final exam to be about the same idea so we can block the day?
If you
block the time, I don't mean that.
If you plan on taking that long to do it, then yes. I was a little surprised. I think I'm used to people having to finish it in 3 hours. So originally, I was planning on having a 3-hour time limit. And then, yes, that's good, Kaitlyn. That means that you're getting your money's worth here, I think. I was going to put a time limit on the exam, but I was always a very slow worker when I was in college. So I wanted to give you guys the extra time. Unfortunately, one of the things I've learned about extra time is if you give students an infinite amount of time to take a test, they will take an infinite amount of time to test. The only thing that I knew was going to stop you was that at some point you were going to just get tired and fall asleep. And so that's kind of how I planned it, right? Hopefully you'll understand how the game is played and it will be easier the second time around. We'll see. We'll see. All right. Today we begin what is in your books, chapter 15, and it's a general lecture on stars. Up to now, you've learned how the sun works, and you should have a vague idea about the layers of the sun, and I think we culminated before the exam in learning about the nuclear fusion that takes place in the core of the sun. So let's just start with like a little memory jog. What do you guys know about fusion in the core of the sun? You could tell me what elements are being fused, or you could tell me the name of the reaction sequence. You could tell me anything intelligent about nuclear reactions in the sun. Something, anything?
Isn't it hydrogen and helium?
That's right.
And they do a little thingy and they make a lot of energy.
They make a little bit of energy a lot of times. They make a little bit of energy. Remember, you're only producing 2 gamma rays. It's a total of, I don't know what it is, a few mega electron volts or something, but the sun is so stupid big that there's bazillions, kabillions of reactions happening per second. Okay, hydrogen to helium fusion. The name of the reaction, by the way, is called the proton-proton chain, and you would be wise to remember it, okay? Let's learn about some other aspects of stars. We're going to take what we know about the sun and we're going to apply it to stars around the galaxy. So I'd like to start by sharing my screen and sharing some slides with you. Let's see if I can do that. Okay, so I want to talk to you guys for a second about some practical fun stuff about how we observe stars, the telescopes and the equipment that we use. First of all, when you guys look at stars, what makes one star different than another? If you look at this field of stars with your eyeballs, what are the two main differences that you see between one star and another star? So I'm going to write stars differ observationally maybe I need to be more specific. What makes this star different than this star?
Color.
You said color, Christopher?
Yeah.
That's if you said color, sorry, it was a little weird, the audio. Devin, blue shift and red shift is going to be a thing, but that's not something you can see with your eyeballs, okay? So put that on rest for a second. Stars differ observationally by color. That's one of the main differences. So let's write, sorry, I'm trying to go to speaker view. By color. Excuse me.
Bless you.
Yes, Cameron for the win. By brightness. Very good, thank you. Cameron, you've distinguished yourself in my eyes today because I was thinking that you guys were going to say something incorrect. I was worried that someone was going to say size. It does look in some ways like this star is bigger than that star, but that is an artifact of photography. As a star becomes brighter and brighter and brighter, on photographic film, the brighter the star, the more exposure to the photographic paper they give, which has the artificial effect of making the star appear bigger. But this thing that you see here, this disk is not the size of the star. Like, that's not the top of the star there, and that's not the bottom of the star. This is an artificial disk caused by diffraction. I don't know if you guys know what diffraction is. I tried telling you last time. It's a bit abstract. It's the spreading out of a wave as it passes through the hole of your telescope. So stars differ by brightness and they differ by color. And after that, there's only one other way. Oh, the weird green blob is probably something called a planetary nebula. I'm going to teach you about planetary nebulae eventually, but they are clouds of ionized gas left over when stars die. And they are very, very beautiful. They're some of my favorite things in space. The pigeons, I lost you there, one sec. Okay, well, whatever. Anyways, there's a third thing that you can do. And you can also take spectroscopy on stars, and that's going to turn out to be a big issue. So the third thing is the spectra of stars. Do you guys know what type of a Kirchhoff's law spectrum a star produces? In a way, I've shown you one before, but you may not have thought about it or processed it. The sun is a star. What type of spectrum does the sun produce?
Black body.
Close, Christopher. I can forgive you for saying that because it's almost a black body, but technically it's not. Maybe we should look at it together again. At my old school, Boston University, they have a nice heliostat, solar spectrum BU. Someone chatted something, but I don't know what they said. This, my friends, is the spectrum of the sun. Oh, can I move slightly over? Yeah, sorry. What? Oh, yeah. What type of spectrum is this?
Absorption?
That's right. It's very important before we go forward today that you know this thing. All stars produce absorption line spectra. Absorption line spectra. And today I want to teach you about how these absorption lines are produced. Okay, the spectra of the stars. Absorption line spectra. And these differ from one another, and that's how we are going to classify some stars. This is observationally. This is when we look at stars. In reality, there are 4 key properties of a star that determine its physics and that make one star different from another. And the 4 key properties of a star that we would like to determine are its mass, its luminosity, its radius, and its temperature at the surface. I call it MLRT. If you know these 4 properties of a star, you understand the physics of a star, you know how long it's going to live, you know whether it will turn into a black hole. And the range of values is interesting in its own right, as I will try to convince you. By the way, the job of an astronomer is to go from this, which are observational properties of a star, to this, which are physical properties of a star that you want to know. And we have to work very hard. We have to mine data to learn these properties of a star. May I erase? Okay. By the way, on that note, from now on, when we classify stars, I'm going to start using new units for mass and luminosity and temperature. We're going to start using solar units, okay? So introducing what are known as solar units to measure stars. 1 solar mass is 2 times 10 to the 30 kilograms. 1 solar luminosity is 4 times 10 to the 26 watts. 1 solar radius is 700,000 kilometers. And although we don't usually use solar temperatures, you could say that the temperature of the sun at the photosphere is 5,800 Kelvin. Please note that this is the temperature at the photosphere, not the core of the star. Remind yourself that the photosphere produces the light that we will see from Earth with our telescopes. Speaking of telescopes, how do we collect this light? Well, in the old-fashioned days, astronomers just looked through telescopes, right? That's how they went about doing things. And when you look through a telescope, your eye can detect differences in brightness, but it turns out that your eye is a sort of crappy light detector. Your eye has a logarithmic response to light, which means objects that are twice as bright don't necessarily look twice as bright to your eye, and your eye will eventually saturate. With the advent of photography, people realized that they could capture more light and measure it quantitatively. So here's a couple of cool old-timey pictures. This is Clyde Tombaugh, the young man who discovered Pluto in 1931. And in the old days, just like a camera has, astronomers would spend the night at their observatory putting photographic paper in at the picture plane of the telescope. You'd have to spend all night exposing the photographic paper, and every observatory would have a dark room. And after you were sleep deprived from staying up all night, you'd then go in the morning bleary-eyed and you'd try to develop these photographic prints and see if you had any good pictures for the evening. I'm old enough where I can just barely remember looking at photographic negatives when I was in graduate school of galaxy clusters and things, and they were actually kind of beautiful and artistic. However, photographs are not necessarily great detectors of light. I believe a photograph only absorbs about 15% of the radiation that strikes it, and that means 85% is bouncing away into space or just heating up the paper or something. At some point with the digital revolution, people developed these very sensitive cameras called CCD cameras. And a CCD stands for charge coupled device. It's kind of like a computer screen in reverse. You have a little wafer of silicon with all of these pixels. And when a photon comes in and hits one of the pixels, it kicks a couple of electrons off, which are stored in a little well. And then every second or so, the computer reads the electron values off of the chip. I guess I don't have to get into all this, but CCDs are basically like the equivalent of digital cameras. Each of you has a CCD right here in your cell phone. If you enjoy taking selfies and pictures for Instagram or whatever, you're using a CCD. And by the way, they were developed by astronomers in the 80s and 90s. I want to show you one as kind of like a show and tell for class here. So just give me a second. Here we go. So here's one that I use sometimes when I take students out to do imaging. It's an ATIC camera. And it's just cool for you guys to learn about this stuff because this is how astronomers do it. If you guys look in there, can you see that little silicon wafer chip? That's the CCD right there. And that captures the light. This housing unit is designed to cool the chip down electrically because the electronics, when they heat up, radiate like black bodies and they give off infrared light, which can contaminate the CCD. So usually you try to cool these things to very, very low temperatures. Guys, I got to tell you, when I was a little shaver, when I was in college like you guys, and I was in Arizona, and they took us up to use this giant telescope on Mount Lemmon. I think it was a 61-inch telescope. It was like the size of a school bus. Their CCD chips were giant, and the telescope is so big that to activate it, you had to get on these hydraulic platforms and like pull levers and bring yourself up to the telescope. And then you'd wheel out a tank of liquid nitrogen and inject it into the CCD chip. It was like being in Star Wars. It was so freaking cool. So it's really exciting when you actually get to use this knowledge and go out to a telescope. Very, very fun stuff. Had this been a normal semester, I would have invited some of you out to the telescope to actually take some pictures with me, but COVID, so whatever. We'll get around to it someday. For now, I want you to know about this stuff because I want you to understand there's a process by which astronomers capture light. And by the way, you know, sometimes when you see those cool Hubble Space Telescope pictures, you see these pictures in Astronomy magazine. I probably have a copy here somewhere. I just saw it the other day. Oh, they're right here. Yeah. When you go on the internet and you look at these mind-blowing pictures of space, you tend to think that all of these photos were taken by the world's greatest and fanciest telescopes, like the Hubble Space Telescope or the Keck Twin Binocular Telescopes. But it turns out a lot of these amazing, mind-blowing pictures of space are actually just taken by grumpy old men who are amateur enthusiasts, and they've got like a cool telescope rig that they put out in their backyards. And this is what a backyard rig would look like. You could have a 16-inch telescope. This guy's got some cool gear here because he can look in through his eyepiece on this side, and there's his CCD camera, so he can take some cool pictures. And he probably sits out there in his backyard at night, on a clear night, just drinking coffee and hiding out in his little garage, taking some cool pictures of space. And one day you may find yourself similarly enthused about astronomy that you want to do something like that as well. Yeah, good old XP. Okay, so let's talk a little bit about the brightness of stars. And I want to start off by reminding you that when we think about stars, we're measuring a very small amount of radiation because the stars are extremely far away. And the difference between luminosity and brightness is best described by our old friend, the inverse square law. So I want to start today with a simple kind of problem like the kind you would have had to do on the test. Does anyone know what the closest star to the sun is? I mean, I, as a science fiction nerd, knew that before I got to college, but I don't know if you guys do. Like, it comes up.
Isn't it Alpha Centauri?
That's right, Christopher. And how far away is Alpha Centauri?
Is it 4 light years?
Very good. Look at that. See, I knew someone would know it. It's 4.4, Christopher, but that's great. So I want to play a little math game with you guys. And let's just ask the question, how bright is a star? Obviously, they have a variety of brightnesses, but we'll take the closest star to Earth, Alpha Centauri, is located at a distance of 4.4 light years from Earth, or from the sun. It doesn't really matter. The 1 AU doesn't matter. It turns out that Alpha Centauri is also special, Christopher, because it has the exact same luminosity as the sun. Actually, the real truth is that Alpha Centauri is a binary star. Actually, it's a trinary star system, but I don't want to overwhelm you. Let's say it's a binary star system. Both stars in the binary are about the same luminosity as the sun. Okay, so let's use the inverse square law to do this. You guys will remember that there's a version, brightness is luminosity over 4 pi d squared. I was talking to Austin offline this week, and he said this stuff really kicked his butt on the exam. So this could be worthwhile going over again. Do you guys remember what the units are that we want for brightness? What do we measure brightnesses in?
Watts.
Watt.
Watts or luminosity? Sorry, Cameron,
Oh.
not joules.
Hertz.
Nope, that's frequency. We want brightnesses to be measured. No.
Wait, was it watts per second?
Not watts per second. You got a d squared there. I was hoping you'd figure it out on your watts per meter squared, Devin. Yes. Star Child to the rescue. Okay. Watts per meter squared. Let's write that down. So what does that mean about our distance of 4.4 light years? We got to convert it. Chris, are you down to help me with that?
Or other Chris.
Which one are you talking to on that?
Oh, sorry. You, Chris Heredia.
Okay. So for light years, we'd have to do 4.4 light years.
Correct?
The X and then the bar.
Yep.
Then you want to put light years on the bottom.
Yep.
And let's see, kilometers on top.
Okay, sure. And do you have a conversion for that?
Yeah, 1 light year is 9.5 times 10 to the 12 kilometers.
Nicely done, sir. And now what?
We want it down into meters, so we're gonna have to do another X on a bar. Put kilometers on the bottom, meters on the top.
Ratio?
And that's 1 kilometer equals 1,000 meters.
Guys, from now on, Chris did exactly what I wanted him to do, and he did it flawlessly. From now on, I want you to remember that 1 light year is also 9.5 times 10 to the 15 meters. That conversion will speed things up going forward. Okay, punch him up. What do you get? Is it warm out today? I'm really hot.
Yes.
Okay, I'm sweating.
4.2 times 10 to the 16.
Meters, right?
Yeah.
Okay, let's put this into the inverse square law. The brightness will equal the luminosity of the sun, 4 times 10 to the 26 watts, divided by 4 divided by pi divided by 4.2 times 10 to the 16 meters squared. Punch them up. Let's see if you guys can handle this. I might actually put on the air conditioning. Let me see here. Do I need that? It's 73. Maybe I'll just open a window. That's going to make some noise, but we'll try it. Okay, what'd you get? Well,
1.8 times 10 to the -8.
I'm just going to say 2 times 10 to the -8. And the units?
It's watts per meter squared.
Did anyone have trouble getting that number? Because I know somebody out there did. I already know someone screwed this up. No? You guys got it? Oh, cool. All right. Arunsak, you got it? Let me see what's happening in chat town over here. Okay. Okay, cool. There's a point to this problem, but I'm not sure if you guys understand it or not. The point is this. Stars are dim. Right? The point is that stars are not very bright. Otherwise, you wouldn't need light bulbs in your house because starlight could just illuminate your home. Perhaps if we lived on a planet at the center of the galaxy or around a globular cluster, the starlight would be bright enough for us to illuminate our homes, but we're not there yet, okay? For the most part, we get a tiny, wimpy, minuscule little trickle of light from stars. And from that little pinprick of light, we need to understand everything we can know about stars. However, if you guys think about it, the brightnesses of stars are usually not something you calculate. And the reason why is because of this thing. A CCD, a charge coupled device, this chip is so sensitive to light that modern CCDs can capture 99.9% of all the photons that it is hit by. In other words, this quantum device is so sensitive to light that I can literally, can you guys hear that? This is definitely not going to work with the window open. Well, fuck you very much. Okay, sorry, it's madness downtown. So what I was trying to say is this CCD is so sensitive to light, it can literally count every single photon you receive from a star. That means you can directly measure the brightness. You can measure the radiant energy of a star with a camera. Now I ask you guys, what is more fun? Sitting inside and doing math or going out and playing with your telescope? Obviously, going out and playing with your telescope is more fun. You would never calculate the brightness of a star if you could go out and measure it. B is an observable. So writing the formula in this way is pointless and useless for astronomers. Now it's time for you to realize the real true importance of the inverse square law. Let's rearrange it. Can I erase? I need board space here. I'm erasing. The inverse square law can be transformed into its true form, a formula known as the luminosity distance. So there's the inverse square law. Brightness is luminosity over 4 pi d squared. And we want to transform it into something known as the luminosity distance. It turns out that one of the hardest things to measure in astronomy is the distances between the stars. You can't just tiptoe out to Alpha Centauri with your meter stick. You have to use tricks and stratagems to learn that it's 4.4 light years away. An especially beguiling problem goes like this. If I see two stars, and one star is bright, and the other star is dim, I can think of two different reasons why these stars would have differences in brightness. It could be that this star is closer than that star, and the closer star will therefore be brighter. It could also be that these two stars are the same distance away, but that this star is intrinsically more luminous than that star. And in science, we call this a confound, two competing variables that we want to tease apart. Let's solve for the distance by doing some algebra. You flip the d squared up, you flip the b down, and then you take the square root. And this is your formula. The distance to your star is the luminosity of the star over 4 pi b. This is a critical formula in astronomy, and I'm going to explain what it means just in case you don't speak math. It means the following things. I can measure B with a CCD. So if I knew L, I could find D. Wow, that kind of rhymes. I'm sort of an astro poet now. Okay. I can measure the brightness with a CCD. If I somehow knew the luminosity of a star, I could compute the distance to the star. So what's my job? My job is to figure out the luminosities of stars. But that's not a very easy thing to do because, as you no doubt have forgotten, and I will remind you, the luminosity of a star is its total radiant output of light in all directions. I can't fly with my flying saucer out to Alpha Centauri and surround it with a Dyson sphere and capture all those photons. That's not a very easy thing to do. Instead, I'm going to have to do a process that sort of resembles building a tree fort. I'm going to find distances to the nearest stars first, and I'm going to measure all of their luminosities. And once I know the luminosities of stars, I can then start computing distances to more further stars. This is something known in astronomy as the cosmic distance ladder. It's a mechanism by which we leapfrog from one star to another, from one galaxy to another, trying to find the distances along the way. This is your first step into that world. So now I'm going to teach you some of the techniques that we use to find the distances to nearby stars. Ratchet and clank. I like it. I like it. Let's talk about parallax next, okay? Parallax, first of all, I want to show you guys this picture just to get you an idea of what's going on. In our own galaxy, there are a handful of stars which are closer to us than other stars. And we sometimes refer to the stars near the sun as the local solar neighborhood. And I thought it might be fun for you guys just to kind of see a picture. So here's our sun, Sol, and you can see Alpha Centauri is 4 light years away. But you'll notice that many of the stars in our neighborhood, they have proper names like Vega and Altair and Denebula and Sirius. That's because these stars are close to the sun, they have some of the brightest brightnesses in our sky. And therefore, they have special names going back into antiquity. So a lot of the stars, I don't know if you guys knew about Vega or Fomalhaut, so probably not, I guess. But I certainly have heard of Castor and Pollux. They're the twin stars in the constellation Gemini. And I know people love their astrology bullshit. So maybe you've heard of Castor and Pollux before. Tag yourself. Love it. Okay, wrestling. These are the stars that we're going to start off finding the distances through, through a technique called parallax, okay? Parallax is an angular shift in the position of a nearby star due to the motion of Earth. Let's all do a quick experiment in parallax together, okay? So I think I might have had you do this once before. Everyone put your thumb out at arm's length, okay? And now close one eye and note the position of your thumb against my blackboard or something. And I want you to blink your eyes. Come on, Kaitlyn, be a sport. Blink your eyes back and forth. What do you see your thumb doing? Could you see it shifting in its angular position? That's parallax, left, right, exactly. Let's draw the picture because I'm going to have you understand it mathematically now. We're going to use the two L's, Cameron, parallax. We're going to need this for our homework today as well. Okay, so parallax, we sometimes also call it a parallax shift. And because parallax, that's okay. Oh no, oh no. Yeah, computer issues are the bane of online teaching. The parallax shift is an angle, and I am going to bust out another fancy Greek letter on you guys. I like to use the letter rho. It kind of looks like a curvy P, and it's fun to write. The Greek letter rho will represent the parallax shift, and it's going to be measured in arc seconds, okay? The parallax shift is an angular displacement in the position of it has to be a nearby star due to the motion of Earth. The key idea, the whole point of the parallax shift is it's used to measure the distances to stars. It is a key technique because it only depends upon geometry, not on any other more complex physics. That means it's very, very safe, okay? It's reliable. And it's an easy concept that we're going to draw out together. Okay, so I'm going to start by making a circle which represents the orbit of Earth, okay? I'll place the sun at the center of the circle. So there's the sun. And Earth is orbiting around the sun. I'm going to pick two positions. I'm going to pick a position where it's here, and I'm going to pick a position where the Earth is there. I would say that's roughly, what, 3 months apart, because it looks like about a quarter of a year. Does that make sense to you guys? 3 months apart? Okay. Let's say there's a nearby star like Alpha Centauri. Let's put that in the middle. And just for funsies, I'm going to make Alpha Centauri red. And now let's imagine that there's a more distant constellation. Everyone knows the constellation of Orion, so I'll draw that over here. So we have Orion as 2 stars, 3 stars in the belt, and then his kilt down here, okay? I want you to imagine how the red star will look compared to the more distant stars in Orion if we observe the red star 6 months apart. Here, the star will be located somewhere near the belt of Orion. Three months later, I'll notice the star has shifted its position below the belt of Orion. Okay. Let me change the position of my star to exactly where the 2 lines intersect. I could have drawn that a little better. So there's my red star. Okay. Now, I want you guys to remember that this distance here is always going to be 1 AU. Well, you said it, not me. Okay. This is what it would look like if you could observe parallax shifts over the course of, say, 6 months or so. You'd notice that some stars in the foreground, I'm sorry, some stars in the foreground, they're having an extreme parallax shift, but you'll notice these stars in the background aren't shifting as much. So the greater the shift, the closer the star is to Earth. And this is just a reflection of Earth's orbit around the sun. Okay. Bring it around to, let's use the small angle formula. When we measure the parallax shift, we measure it here. So this is the parallax shift because we measure the shifting position of the star relative to the stars in Orion. Can you guys believe if I tell you that this angle here is also the same as this angle here? I think they call those alternate interior angles, right? Like if you take two straight lines and you make an X, those angles always have to be equal to each other. What is XD? I don't understand. Okay, I don't speak LOL, so you got to go easy on me. So let's just say the answer is yes, that you believe that this angle and that angle are the same angle. I am now going to apply the small angle formula to this problem. Remember that D is the distance from the nearby star to the sun, okay? So I'm going to use version 2 of the small angle formula. And it's going to go S, actually, okay, S equals, instead of alpha, I'm now going to use the parallax shift times D over 206,265 arc seconds. You guys will remember this is what I called the small angle formula part 2. However, in this case, do you guys understand what the S is? What is the S in my diagram? I think it's helpful if you guys can identify it. What is S in this diagram?
Angular size.
False. Rho is the angular. Rho is the angular. By the way, it's not angular size. In this case, it's angular separation from there to there, right? Or from there to there. Can you guys see my mouse? Can you see this mouse? No. Okay. This is the angular separation between these two stars, but it's also the angular separation between the Earth and the sun right there. S was the size of a star when we were measuring the physical size of a star. But when you measure the separation between two stars, S is the physical separation, right? It's a length. So what is S in this diagram?
A distance.
Which distance?
Between two stars. Dang.
Well,
Like on the diagram, you have the two red stars like kind of projected onto Orion. So it's the distance.
right. Okay, it would be that, but the problem is, Christopher, we have no freaking clue the distance between that star and those stars. So that's useless.
So
What if
would
we
it
reverse
then
it? That's
like
also,
the distance between the sun and the Earth,
which is always,
the equivalent to that?
well, the distance between the sun and the Earth does not change. So that's a fixed value of 1 AU.
1 AU.
1 AU, right. So this is always going to be equal to 1 AU. Now, I'm going to go up here and I'm going to do a little geometry on this. What do we want to know? What are we trying to solve for? What's our motivation as a character here? What is the quantity we are hunting for?
The distance between those two red stars.
We're hunting for the distance from the sun to the nearby star of Alpha Centauri. That's what we're hunting for. We're trying to measure the distance to a nearby star, D. So let's solve for D. So I'll flip up D. I'll get 1 AU, 206,265. All right. So the distance to the star is 206,265 arc seconds divided by the parallax shift times 1 AU. And that's it. I measure the parallax shift and I get the distance. Except there's a new twist here. I'm going to throw a boomerang into this game. This formula is already what I want. By the way, if I put my parallax shift in arc seconds, what will the units of my distance come out to be? Let me ask that again. If I measure a parallax shift and I measure it in arc seconds, what units will the distance to my star come out in? Oh, I'm sorry, is that too tough for you?
Would it be like arc seconds times AU?
No, because you'd be, okay, look, Alpha Centauri has a parallax shift of 0.75 arc seconds. What will your units come out in now?
Arc minutes.
No, Blair understands me. Blair, you may be a troll, but you understand me. Arc seconds will cancel out and AUs will be left behind. Now, the point I'm trying to make is, are AUs a good unit to measure distances between stars? Yes or no?
No.
No. AUs are appropriate for a solar system size distance. What would be more appropriate?
Light years.
Yeah. But I've got to tell you something. There's a big secret in astronomy that you're now prepared to learn. Light years are for little kids and news journalists. Astronomers don't actually use them. Astronomers think of light years as cheesy. They use a different unit, which is, yes, Cameron, the parsec, okay? Now, do you want to know what probably the most useless unit is in the entire system of units? Even worse than Fortnite beards? I'd say probably the most useless unit, well, miles are pretty bad, but you know what's even worse than miles is yards. And the reason why a yard is the stupidest measurement is because a yard is only about 3 feet. So anything that you measure in yards, you could just as easily measure in feet with no real change in goodness. So it may surprise you that I am about to introduce the space yard. Introducing the parsec. So a new unit of distance called the parsec. And I'm going to introduce this in a really weird way, okay? I need to erase this. Sorry, I got to erase that. Okay, 1 parsec is 3.26 light years. And that pretty much makes the parsec the equivalent of a space yard, okay? The parsec has a definition that I know you're not going to like. And here's how it goes. 1 parsec is defined in the following way. The distance at which 1 arc second subtends 1 AU. The meaning of that is that you take an arc second and you let the arc second roll out into space. And when the arc second has gotten so far away that this distance is 1 AU, 1 arc second, that distance is defined as the parsec. In essence, this creates a secret version of the small angle formula. I call it the small angle formula part 3, and it's a very secret version of the small angle formula. S equals the angle times the distance. if you measure the distance in parsecs and the angle in arc seconds, the separation will come out in AU. You might think I'm just rambling here, kids, but if you were smart enough to write this down and remember it, this will save you so much time on your final exam. If you know the secret version of the small angle formula part 3, you can solve many, many test questions in a very short amount of time. This is how you make sure that you're not up all night and day working on your exam. I can't tell you how important that is. Okay, there's another weird thing about the parsec. A parsec is not only equal to 3.26 light years, but the real reason we designed the parsec this way is 1 parsec happens to be equal to 206.265 AU. That's the key conversion right there. Because watch this. I'm about to do a conversion from AUs to parsecs. Not only do AUs cancel out, this is some sleight of hand magician shit. You probably don't even understand what I'm doing. The 206.265 cancel out. That's right, Kevin. The whole point in this was to make the world's laziest astronomy formula, which is the distance to your star in parsecs is 1 over the parallax shift in arc seconds. This is a key legendary formula in astronomy, and it's how astronomers measure the distances to nearby stars. Let's try an example by looking up the parallax shift of a famous star. Do you guys remember what the brightest star in the sky is?
Betelgeuse.
No, it is one of the brightest stars, but it's not the brightest. Betelgeuse is a little Sirius. You can actually get parallax shifts right from the internet. Where is it? It's 379 milli-arc seconds. So let's try a problem here. Let's try a problem together. Try to keep up with me, guys. 0.379. The star Sirius has an observed parallax shift of 0.379 arc seconds. Find the distance. Now, I'd like to use this opportunity to teach you a new key. So obviously, this is going to be pretty easy. The distance is just 1 over 0.379 arc seconds. But can I recommend a method by which we're going to punch this in? I want to introduce you to a new key. I've got hair in my eye. All right. A new key on your calculator. Let me open up my Logitech doodah. Logitech capture. Okay. The key is called the reciprocal key, and it's located just above the closed parenthesis key. And I'm going to want to use this key later, so I'm introducing it now. Trust me that there's a reason for all the things I do, even that long, hard test. Okay, I'm going to focus up to about 30 something. Okay, now watch. We're going to type 0.379, and we're going to hit reciprocal by doing shift 1 over x. My final answer is 2.6 or 2.64 parsecs. Notice I kept the same number of significant figures in and out. How many light years is that, students? How many light years? What's my conversion?
It's almost 6 light years.
Try it.
5.96.
It's 1 parsec is 3.26 light years. But you're basically saying 2.6 is closer to 3, so you should have said 9 light years. I think were you doing 3 times 2? Yeah, it's 8.6 light years away. You will be doing this on your final exam. Luckily for you, it's pretty freaking easy. You just take the reciprocal, all right? Now I'm going to ask you another question. It looks like everyone's, Stacy, are you done writing? Christopher, I'm going to erase, okay? Do you guys remember what the minimum angle of detection was for the Hubble Space Telescope? That might be asking a lot, but it came up in one of our homeworks. Very good, Blair. Damn, Blair, we got a junior astronomer on our hands. It was 0.05, but I need some units. The Hubble Space Telescope has a diffraction limit of 0.05 arc seconds. That's the minimum angle, right? So my question is, how far out can Hubble measure parallax distances? I think this is an important conceptual question. What do I do? Really? See, I love these kinds of questions. What you have to do isn't hard. It's just conceptually hard. You have to understand what the question is asking. Do you understand what the question is asking, Arunsak? No. Does anyone in the troll audience understand what the question is asking? All right, Kevin, how did you do that, Kevin? Also, Kevin, 20 what? Inches? I hate it when you guys don't put units on things. It drives me batty. Kevin already knows the answer to this question, 20 parsecs. How did Kevin know that? What makes Kevin so smart? Kevin, all right, Star Child. Kevin knows that if Hubble can only observe down to a minimum, he did distance equals 1 over parallax shift. And he argued that if Hubble can see down to a minimum angle of 0.05 arc seconds, then the maximum distance Hubble can measure out using parallax is 20 parsecs times 3.26 light years per parsec gives you about 60 light years. And now I'd like to ask you another question, Kevin, since Kevin understood me. Kevin, what percentage of the Milky Way galaxy can I then explore using the Hubble Space Telescope? Do I have a picture of the Milky Way here? Somewhere I do. What percentage of the Milky Way can I explore if Hubble, the best telescope in the world, can reliably measure distances out to 60 light years.
Isn't the Milky Way galaxy 100,000 light years in
Right.
diameter?
So Kevin, if that was your voice, I guess that would make 60 parsecs basically like this little fucking pixel here, right?
Yeah.
And that basically means parallax will only get you the distance to like 0% of the galaxy, just a handful of crummy stars nearby. So the thing that I would be worried about is, well, how am I going to find the distance to all this cool stuff like the supermassive black hole or weird stuff over here? How do I get that? Well, now I'm going to tell you a little bit about the history of parallax. Now, Cameron probes, we haven't even got to the nearest star, Alpha Centauri. We haven't probed anything. When I was a student, in the 80s, they developed this spacecraft. I want to tell you guys a little bit about the history of parallax measurements. I don't know, you probably don't care, but I'm telling you anyways, because I want to entertain myself. In 1989, they launched a satellite called Hipparcos. And Hipparcos used tricks of geometry to maintain a 0.001 arcsecond resolution for parallax shifts. That's 1 milli-arcsecond. That allowed them to measure reliably distances out to 3,000 light years, and there was a catalog of 100,000 stars called the Hipparcos Catalog. And what was cool is every scientific paper, whether it was the age of the universe or whether it was how old is Betelgeuse, they all had to use the distances based on Hipparcos. So every science paper had to reference this space mission because this catalog was everything we knew about the galaxy. In the last few years, we developed this crazy satellite known as the Gaia Satellite, which launched maybe 3 or 4 years ago. And it totally transformed astronomy in fundamental ways. The first cool thing about it is it had the world's biggest CCD chip on it, a sensor that was 1 billion pixels. That's a 1 gigapixel camera, okay? Here are the technicians working on it. And it used all this high-tech trickery in engineering, and it bounced starlight off of mirrors. And, you know, this would be a whole talk in itself to explain how the Gaia satellite works. They also plopped it at a Lagrangian point, basically in deep space, far from Earth. And it somehow could obtain a resolution of 10 micro arcseconds. The whole, you might be missing the point. The whole purpose of this satellite is to measure parallax shifts and nothing else. It could measure distances out to 300,000 light years. As Kevin pointed out, the galaxy itself is only 100,000 light years. So this could measure distances out to extragalactic sources like the Small and Large Magellanic Clouds. And it created a catalog of 1 billion stars. We basically can perfectly measure the distance to almost every star in the Milky Way. This was such an important result in astronomy that overnight, it changed the age of the universe. It changed so many interesting fundamental parameters in astronomy. So this Gaia space mission is a big deal. And one of the secret things about it that people don't always realize is because we can now measure the distances to stars very precisely, it opens up a whole world for small telescopes and small observatories like the Jacobi Observatory to do cool publishable science with only a 16-inch telescope. So I don't know. I wanted you to hear about it here in case you ever see this in a newspaper or something. Okay. I have time barely for one more module, but we need it for our homework today. So I want to teach you about one more thing before we stop, okay? And just one more module, if you can bear with me. The stuff that we are going to do after this is going to require us to have new methods of measuring the brightnesses of stars. But when I say new methods, I'm really talking about some very ancient old methods known as the magnitude system for stars. So let me introduce to you a new way to measure the brightness of stars. And it's not a new way, It's actually an old way. It's the oldest way that's in existence. It's known as the magnitude system. And the magnitude system was developed by an ancient Greek known as Hipparcos. Hipparcos was considered the greatest of the Athenian Greek astronomers. And he developed a ranking of stars by eye, a ranking of stellar brightnesses, known as apparent magnitude. In our class, we will use the symbol little m for apparent magnitude, lowercase m. Apparent magnitude is a basic and simple ranking of the brightnesses of stars. He took the brightest star he could find, and he called it a first rank star. By the way, just a question. Does anyone in this class know what magnitude means? What does that word mean, magnitude? Nothing?
Does it have to do with size?
It actually just means a number without units. If you are 2 meters tall, the magnitude is 2. It's a number that, this number intentionally has no, you know what this is kind of like? It's like when you rank your favorite movies. This is number 1, this is number 2, this is number 3. It's amihotornot.com for stars. The brightest star is a rank 1 star. The second brightest star that he could observe was a rank 2 star. The third brightest was a rank 3 star. And then there was a 4th rank and a 5th rank. And Hipparcos went all the way down to 6th ranks. So he broke the brightnesses of stars up into 6 rankings. As I mentioned before, it turns out that the human eye has a somewhat logarithmic response to light. It turns out that when we later measured the physiology of the human eye, that a change in 5 magnitudes, so a change in 5 magnitudes is equal to 100 times change in brightness. Something that you guys should know is that Hipparcos didn't measure all of the stars. He even forgot some of the brightest stars. Today, the star Vega, so one of the things that makes the magnitude, one of the things that makes the magnitude system start off really simple but end up being wicked complex is he made the unfortunate choice of using smaller numbers for brighter stars. So when we found stars that were brighter than his brightest star, we ended up with some problems. The apparent magnitude of Vega is 0. The apparent magnitude of Sirius is -1. Oh, and don't forget the sun is a star. The apparent magnitude of the sun is -27. Oops, that sucks. Welcome to the magnitude system. You're not going to like it. But to try to soften the blow, I want to show you guys something. There are these beautiful, it is absolutely crazy, Kevin, and we still continue to use it today for very subtle reasons, which I don't have time to explain to you. But I want to show you guys something kind of cool and pretty. There's a couple of famous stellar atlases that they made in the, I think in the late 1800s. One is the Jameson Celestial Atlas. And there's another one too. What's the other one? They did these absolutely beautiful illustrations of the stars in the sky, and you can get them. You can get high resolution versions of them. I just want to show you a couple because they're so cool. So here's Gemini, and here's Taurus, and they're just really cool, classy things to look at. I used to have them as a screensaver, so every time I'd come into my office. So this is a cool art meets science thing. This guy was a visual artist who did pictographic illustrations of all the constellations in the sky. And there's a legend somewhere down here where he shows you how the magnitudes are ranked with different shapes. Like I think a first magnitude star, so this is a magnitude of 1. He would use this 5-pointed star. I think this is a second rank magnitude star. I think the third rank stars were like this one. These are like the 4th magnitude star, and so forth and so on. He's got a legend somewhere. Maybe it's, let me clear all this. Maybe this one has the key. Not this one either, but this is Gemini. You can get all of these online and look through them sometime. They're really, really beautiful. There's Betelgeuse. Betelgeuse is a 1st magnitude star. Why am I showing you this? Well, one, because I think it's beautiful and awesome, and the illustrations are cool. 2, because I'm trying to impress upon you just how old and ancient the magnitude system is. We've been measuring, oh, there's Castor and Pollux, which are about a rank 1 star. We've been using the magnitude system for so long that it's cooked into the very DNA of astronomy itself. You'll often see stars ranked in terms of their magnitudes. Okay, now comes the part where I have to drop a really yucky formula on you. In our homework today, we're going to have to measure magnitudes and translate them into brightnesses. And we're going to use this fact. If you change from a magnitude 1 to a magnitude 6 star, that's a ratio of a factor of 100 in brightness. So now let me write a formula on the board that's probably not going to be so pleasant, okay? Okay. Let's say you've got 2 stars, and let's call the bright star the A star, and let's call the dim star the B star, just for kicks and giggles, okay? If I want to know the ratio of the brightness of the A star to the ratio of the brightness of the B star, if A is brighter, I'll always take A divided by B. That can be translated into magnitude by taking a factor of 100 and raising it to the power of the change in magnitudes divided by 5. That is 100 raised to the power of MB minus MA over 5. Where I have to subtract B minus A because the dimmer star has the bigger magnitude. Like I said, you aren't going to love that formula, but you got to use it today, so I wanted to get to it before class ended. I want you guys to remind me that next time we do class, I'm going to teach you about an even more hideous version of magnitudes called absolute magnitude. But I'm not going to get into it now because it's too many words. Could you write that in your notebooks and I can ask you about it next time? Okay. We ready for some tea time or what? All right. Let's take a 15-minute break. Then we'll do homework 15. Homework 15 is not so bad, okay? We're going to crush it. I'll see you guys in a little bit. Hi, guys. We ready to crush homework 7 or what? Kevin, what formula are you talking about, buddy? You talking about a magnitude formula? Are you talking about distance modulus or are you talking about NK3? I'm not sure. So do we want to stay on break forever, or do we want to get our stuff done? What do you guys think? Arunsak, Stacy, since you're here with me, can you guys help me get the numbers? Stay on break forever. Well, I'd like that too, Kaitlyn, but I've got to torture you more. That's my job. Okay. This won't be the worst homework we've ever done. I promise you guys. Some of the questions are real fast. So let's do the usual stuff we do. Put our name. Always class 10, whoop. People keep writing me emails and they keep saying stuff like, hey, are we doing this thing tomorrow? Can I do homework 1? I'm just like, what class are we in? I don't remember everybody. So you got to help me with that. 1020. This is homework number 7, I believe. It's chapter 15. And who's got them numbers for me?
I do.
Okay.
It's at number 45, 54, 55, 56, and 57.
Okay. I want to warn you guys that we're only halfway through our lecture on chapter 15. But I did cover 3 out of the 5 problems, and the other 2 won't be a big deal for reasons. That's fine, Arunsak. I'll explain in a minute. The first question that we're going to do is about a famous diagram called the Hertzsprung-Russell diagram. And I didn't quite have time to get to it today, but it's not, well, it's complicated in that there's a lot going on, but it's not that hard to understand. So let's jump ahead to it. You guys can kind of think of this diagram, and I'll set it up for you right proper next time. This diagram is kind of like, it's the equivalent of the periodic table of the elements, except for stars. This diagram tells you everything you could ever need to know about stars and helps you compare their 4 fundamental properties. Do you guys remember what the 4 fundamental properties of a star are?
Luminosity, diameter, forgot the rest.
Mass and temperature. MLRT. MLRT. I want to point out before we begin this problem that you can get all of those things from the Hertzsprung-Russell diagram. Temperature is plotted on the x-axis, although it's a little bit weird because the hotter temperatures go to the left, 3,000 Kelvin to 30,000 Kelvin. The luminosities of the stars increase vertically, so you've got L here and you've got T here. The radii of the stars increase diagonal to the right. And the masses of the stars are written in this kind of, what would you call this, magenta? They're kind of in a magenta color, and they measure diagonally up to the left on the main sequence. So M goes diagonal to the left, radius is diagonal to the right, temperature is to the left, luminosity is up. Okay, Stacy, could you read me the very first question, title and all? Chapter
Sorry,
15.
accept to get there. Yep, number 45. Interpreting the HR diagram
Okay.
using the information in figure 1510, describe how Proxima Centauri differs from Sirius.
Okay, we're going to make this a compact table. Get out a ruler or a straight edge, and I want you to follow along with me for the answer, okay? So we'll have the parameters in the first column. We'll do Proxima Centauri in the second column. We'll do Sirius in the third column. We'll do the ratio in the fourth column because we have to compare them. Okay, so we have the property or the parameter. This is going to be Proxima Centauri. I'm going to abbreviate Proxima Centauri as ProxCent. This is Sirius. And here's the ratio. Obviously, we're going to want to get some key properties. I need two more, actually. Okay. I think it would be kind of cool if we could get mass. One of the purposes of this question is to show you just how much information you can get about stars from the HR diagram. Luminosity, radius, temperature, we can also get color, and we can get the estimated lifetime. All right, I'll put the diagram up. First, why don't you guys show me if you can identify where the stars are. I think anyone should be able to draw on this that wants to. I hope I gave you permission to draw. Can you guys, think you guys can take a, let's choose yellow. Circle the two stars with the yellow circle if you can find them. Sirius and Proxima Centauri, where are they?
I don't know if I can draw on it, but I do see them.
Oh, I thought you guys had permission to draw on this, but I want you to have permission to draw on this. Security settings. Annotate unshared content. Yeah. All right. Well, Proxima Centauri is over here. Sirius is over here. Let's start with the mass. Can you guys figure out the mass at the rough, just loosey-goosey, what the mass of Proxima Centauri is?
See 0.0 something.
That's pretty good, but I want you guys to remember 1/10 of a solar mass is the lowest stellar masses. So even though you are correct, Christopher, it's actually closer to 0.08. We're going to just choose 0.1 solar mass units, okay? Okay, let's try to be a little more succinct. Oh, you can't draw, huh? Weird. It says you can. What would you say about Sirius if it's right there? Not quite 3 solar mass units, but
Looks like two something.
Oh, hey, look, you can draw Daniel DaCosta. 1.5 is there and 3 is there. So I'm going to say, since it's a little closer to 3, 2.5, if that's okay with you. But 2 is a good guess as well. And that's solar mass units. Can you guys do that ratio in your head? No calculators for this part. You should be able to do that in your head. What is 2.5 divided by 0.1? Come on, what does 0.1 mean? 0.1, how do we say that? Yeah, Gianna knows It's 25. This is a tenth. So if you divide by a tenth, you have 10 times as much. The ratio is 25 times more mass. Okay, nice, Gianna. How about the luminosities? You get the luminosity off the y-axis, so we could estimate Proxima Centauri here, and Sirius could be about there.
Like 10 to the 1/2 power, or am I like?
This is a logarithmic scale, so you want to be careful about that. 10 to the 1/2 power means the square root of 10. The square root of 10 is less than 10, okay? Remember that 10 is 10 to the 1. If anything, Chris, it's more like 10 to the 1.5. What is 10 to the power of 1.5?
That'd be 15.
No, it'd be 30. 10 to the power. Logarithmic scales are kind of weird like that. What about 30 what though? What are the units?
Like solar luminosity.
Yes. Okay, what about Proxima Centauri?
It's 10 to the -3.
Okay, cool. It's really irritating. Yeah. Stop share. So 30 solar luminosity units. Okay, Gianna, why don't you show these cats how it's done? 30 divided by 10 to the -3. What do you get? No. What does 10 to the -3 mean?
Is it 3,000?
Try even better. All right, someone just said it. 10 to the -3 is 1,000th. Christopher Leonard understands that 30 divided by 1,000th is 30 times 10 to the 3, or 30,000 times brighter. There is a huge disparity in the luminosities of stars. Some are many millions of times brighter than each other. It's crazy. Luminosities are insane. How about the radii? You have to use the diagonals on the diagram. This is a diagonal for 1/10 of a solar radius, 1 solar radius, 10 solar radii. What would you say for Proxima Centauri?
Looks like 0.1 solar radius.
Good. How about Sirius? How would you estimate that?
Looks like around like 2 solar radius.
Yeah. It's like a third of the way up. So 2 solar radii is great. And what would that ratio be? I want to see if you guys are starting to catch on here.
20.
20.
Excellent. I am dying here. I'm choking on something. Let's do the temperatures in kelvins rather than solar temperatures. They have a smallest range of temperatures, so we get that from the x-axis. I want you guys to remember 3000 as the lowest possible temperature that a star can have. And it looks like Sirius is closest to like 9,000 or so. So it's 9,000 versus 3,000. Kelvin, sorry. What's that ratio?
3 times.
Yeah. Notice temperature is the thing that varies the least among stars. Luminosity is the thing that varies the most. Okay, so how would you describe the color of Sirius and how would you describe the color of Proxima Centauri?
Sirius is like a whitish blue.
Right. I'm going to call it white. And Prox?
Red.
Right. Small dim stars tend to be red stars. That's going to be important truth. We don't need a ratio for this. Okay? So. Fudge. Fucking A. Hold on a second. Just put 2 dashes there. Oh, sorry, Christopher. Okay. How about estimated lifetimes? This one we can be real loose with. The lifetimes are in green.
Looks like 10 to the 8.9 for Sirius.
No, we don't have to get, let's just call it 10 to the 9 versus 10 to the 11, okay? What's that ratio? Oh, wait, I did that backwards, didn't I? Did anyone notice? The little stars live longer than the big stars. What's that ratio?
.01.
Or 100th, if we do Sirius. White stars live 100th the total lifetime of a red star. All right, that's it. That's your answer to 45 right there. How are you guys doing? Can I erase or do you need more time? Okay, anyone in the background there? Emily, you good? Nice to see you, Emily. I'm erasing. Emily, are you down to read us 54?
Yeah, 1 second. Let me pull it up. More practice with the inverse square law for light. So loud.
I forgot about the.
Yeah.
Okay. So, what's part A ask?
Suppose a star has the same luminosity as our sun, 3.8 times 10 to the 26 watts, but it's located at a distance of 10 light years. What is the apparent brightness?
All right, this is just like we did in our homework today. Do you guys remember the conversion from light years to meters? Because we have to do that.
9.5 times 10 to the 15.
Meters per light year. Excellent. So can you tell me what the distance is in meters then? If I multiply that by 10, I get
To the 16th.
9.5 times 10 to the 16th. All right, now we're going to find the brightness using the inverse square law. Brightness is luminosity over 4 pi d squared, 3.8 times 10 to the 26 watts over 4 over pi over 9.5 times 10 to the 16 meters squared. You guys are pretty good at this in our lecture today, so punch them up.
3.4 times 10 to the negative 9
Units?
watts per meter squared.
Can someone else confirm that, just so we have two eyeballs on it? Is that what somebody else got?
Correct.
All right, good. Let's move on to part B. No time to waste. When you're ready, Emily.
Suppose the star has the same apparent brightness as Alpha Centauri, 2.7 times 10 to the negative 8th watts per meter square, but is located at a distance of 200 light years. What is its luminosity?
So this is the brightness, and it's located at a distance of 200 light years. Let's convert light years to meters again. Hopefully you don't mind if I do the dimensional analysis for you. 1 light year is 9.5 times 10 to the 15 meters. Why don't you guys punch that up for me? I'm guessing you're going to get pretty close to 2 times 10 to the 16, 17, 18. You're going to get 2 times 10 to the 18 meters, right? Maybe 1.8.
Yeah, it's 1.9, but to the 18th.
Am I crazy for thinking?
All right, now we can rearrange the inverse square law to solve for luminosity. Luminosity is 4 pi d squared times the brightness. 4 times pi times 1.9 times 10 to the 18 meters squared times the brightness 2.7 times 10 to the minus 8 watts per meter squared. Punch that up. Whoops.
One 0.2 times 10 to the 30.
That sounds good. Hold on, I'm putting away my CCD. Wait, 1.2 times 10 to the 30th? Did someone else get that?
Yep.
And I was going to ask you what units, but I already wrote them down. Watts. I'm going to erase part A. Shout at me now if you don't like that. See what's up in the chat world. Okay. Emily, part C.
Suppose a star has a luminosity of 8 times 10 to the 26 watts and an apparent brightness of 3.5 times 10 to the negative 12th watts per meter squared. How far away is it? Give your answer in both kilometers and light years.
Do I have that brightness correct?
3.5 times 10 to the negative 12.
Okay. Which formula do I want? What's the name of the formula that I want, students?
What are we finding? I missed that.
The distance. This formula has a special.
Luminosity distance.
Excellent, Christopher. Excellent. The luminosity distance formula. It's radical L over 4 pi b. Make a nice neat square root. 8 times 10 to the 26 watts. 4 pi 3.5 times. We actually don't need parentheses there. 10 to the negative 12. See what you guys can do with that. I shouldn't need to explain how to do that to you now. You should just know. I guess I'll punch it just to keep an eye on you. Two sig figs.
4.3 times 10 to the 18
Units?
meters.
Now, I know they said they wanted it in both kilometers and light years, but if you ask me, kilometers are totally stupid and pointless. Let's just convert it directly to light years and be done with it. How do I convert that to light years? Arunsak?
Do set it up, X bar. And then what is that? 1 light year. Top, meters at the bottom.
Halloween, are we trying to hustle 1,000 corpses?
And then 9.5 times 10 to the 15.
It's probably
15, right?
15, yep.
I watched 31 the other night.
Wow, it's noisy in your place, Arunsak. That must be difficult to concentrate on this lecture.
Yeah, coffee shop noise.
Oh, are you in a coffee shop?
Yep, I'm
What
at
do you
brew.
think about all
No kidding. Oh, it's loud as F in there. But good on you, son, for going to the coffee shop and getting your class done. I like it. Maybe I should go and teach my class in a remote location. That'd be fun. Except I can't do that. Anyways, what's the answer?
453 light years.
Two sig figs are good. Okay, Emily, part D.
Suppose a star has a luminosity of 5 times 10 to the 29 watts and an apparent brightness of 9 times 10 to the 15 watts per.
Okay, wait. What did they say this thing was?
What do you mean?
Suppose a what has a luminosity of 5 times? A star, a galaxy, what is this?
A star.
Can a star have a brightness of 9 times 10 to the 15 watts per square meter?
No.
Hell no. If a star was that bright, it would be brighter than the sun. It would burn your eyeballs out of your skull. That's a stupid amount of brightness. That's more brightness than at the surface of the sun by a factor of 1 billion. In other words, they screwed up, didn't they, Emily?
Yeah.
How did they screw up? They forgot something. Oh,
Not sure.
no, it can't, Blair. This is the observed brightness. They forgot a negative is what they did. The stars are dim. That's a typo. Blair, it wouldn't matter how close or far it was. The brightness is how much light you're receiving at Earth. There's no such thing as anything on our sky that has that kind of brightness. Whatever, it doesn't matter. Let's just do the damn problem. Same as before. Distance is the square root of 5 times 10 to the 29 watts over 4 pi 9 times 10 to the minus 15 watts per meter squared. If you had plugged in positive 15, you would have found that that star was like 2 kilometers away, which clearly doesn't make any sense.
(2.1 to the 21).
Units?
I got
Meters.
What did you get,
Um,
Christopher?
2.2 to the 28.
Can I get a tiebreaker here? What did Kaitlyn get? What did Stacy get? (45) square root of 45 is half of 45. I think Arunsak is correct, but I'm not sure. What'd you get, Kaitlyn?
I got 2 times 10 to the 43, but I don't think that's right.
Did you
Wait,
remember?
Chris, did you square it?
Chris definitely square rooted it. Kaitlyn did not square root it. She forgot to square root, but
All right, well, now I've got 4.2 times 10 to the 21.
oh,
Yeah, square root that.
Kevin got 2.1 times 10 to the 21 meters. You guys just flat out refuse to put units on your numbers. It's crazy. So it sounds like Kevin, whenever I get 2 people that get the same number, I start to get confidence. I guess I have to do this now because a bunch of you were getting it wrong, right? 5e29 divide by 4 divide by pi divide by 9 exp minus 15. Yes, equals shift square root. Arunsak and Kevin were correct.
Oh, I see what I did wrong.
Okay, good. How many light years is that? How many light years? I want to know where the F Austin.
220,000.
What do you say we all call Austin up on speakerphone and find out why he's not in class today? What is it, 220,000?
Yeah.
Um,
Hello?
hey, Austin, how's it going?
Good, how are you?
Good. The entire class is calling you up because we want to know why you're not here doing homework problems with us. So you're on speakerphone.
Oh, hello, class.
What's up?
Hey, Austin.
Hello.
So
Hi.
So, I mean, I could go on, on the Zoom call, but I'm not going to be very productive in the car. I was in the car in my accounting class, or my management class yesterday.
All right.
Won the Kahoot game, almost got into a car accident. So I decided that.
All right, we don't want you getting in a car accident, but you're going to do your homework later, right?
Yeah, and it's going to be submitted tonight. No bullshit, no late.
Yeah.
None of that crap.
All right, good. All right, love you. Bye. Let's get on with it. Number 55. Kaitlyn, can you read this one for us? Chapter 15.
Yeah, let me just pull it up.
All right.
All right, thank you very much for holding. Looking into
My
this
computer's
today,
being funny on me today.
Oh, yeah. So you were saying.
I did find the overdraft fees.
I'm really worried about the day when my computer goes bad or when the internet is lost, and then I'm going to be really screwed.
See that processing has-
Yeah, hold on one second. My like Blackboard thing totally just won't load.
So I'm actually from
Yeah, Blackboard is the worst. It took me a very long time to do your grades. By the way, I just want to say one more time in case any people joining the class in the background. I tried to do this thing this summer in preparation for this semester where I tried to record like an astronomy lecture in my friend's film studio in East Providence. And I thought it was going to be really, really awesome. And I got all these props. And
Hey, I'm in East Providence.
Yeah, he's got this cool studio over there called, oh gosh.
Thank you. You have a great day.
Fuck, I forgot. Excuse me. I forgot what the name of it was, but it's a really cool film studio and he's a really nice guy. It's like Dan Phillips Studios or something. No, Retina Labs. That's it. Retina Labs. And you want to know what happened? I brought all of this gear in. I hauled it all over there in my van. I had this giant size celestial sphere and I was totally boring, like really not good. It turns out that the only way I'm good at teaching is if I have other humans to talk to, and then I'm more charismatic. But when I tried to like pre-record myself, I hated watching it. It wasn't fun at all. So you guys are an essential part of this equation. That's what I'm trying to say here. Okay.
Yeah, I'm sorry. There's just like isn't loading now. Anything.
That's okay, Kaitlyn. We'll give you a break. Stacy or Arunsak, Stacy, you want to do this for us since it's a little quieter in your house?
Sure. Well, don't say that, but yes, I will happily. We're doing 55, correct?
Yeah.
All right. Parallax and distance. Use the parallax formula to calculate the distance to each of the following stars. Give your answers in both parsecs and light years.
This will be wicked easy.
Good. A is Alpha Centauri. Parallax angle is of 0.7420. I think it says arc seconds, but degrees. I can't see it.
No.
Sorry.
Okay, so let me explain something. Parallax shifts of stars are wicked, wicked, wicked tiny. It would never be 0.7 degrees.
Okay.
They're all less than 1 arc second. Alpha Centauri is the closest star to the sun, and its parallax shift is 3/4 of an arc second. So it's got to be arc seconds. Okay, do you guys remember how to do this? You put your thing down, flip it, and reverse it. It's very easy. Distance is 1/0.7420 arc seconds.
1.35.
Let's do 4 sig figs to keep up with the Joneses here.
1.348.
Units?
AU.
No. Space yards or,
Oh, parsecs.
all right, now let's convert it from parsecs to light years. You guys remember the conversion from parsecs to light years?
Uh, 3.26 light years for 1 parsec.
All right. So how many light years? You can only keep 3 sig figs now because your conversion factor is polluted.
.39.
Okay. When you're ready, Stacy, part B.
All right, 55, part B is Procyon, the parallax angle of 0.02860 arc seconds.
I'm sorry, can you give me that one more time?
Yep, the 0.2860 arc seconds.
Okay, we'll put it right back into that parallax shift formula. Distance is 1 over 0.2860 arc seconds.
.497.
Units?
Parsecs.
Good. And now let's convert that to light years with the same conversion. Parsecs to light years, 1 parsec is 3.26 light years.
.11.3.
Both of these stars are in our solar neighborhood because they're within about 50 light years or so. Alpha Centauri and Procyon are famous stars in the sky. Procyon is in the constellation Canis Minor, the little dog. The little dog and the big dog follow at the heels of Orion as it marches across the sky in the winter. Look for Sirius and Procyon coming to a sky near you. Can I erase? Gotta love parallax. It's the best, easiest thing. Okay. Christopher, did you read us one yet? I can't remember. You want to read us another one? Want to read us 56?
Yeah. The magnitude system.
Here we go.
Use the definitions of the magnitude system to answer each of the following questions.
We're going to use the formula brightness of star A over brightness of star B is 100 to the power of change in magnitudes divided by 5. Excuse me. Okay, what do we got for A, Christopher?
1 sec.
Sure, take your time.
For part A, which is brighter in our sky, a star with an apparent magnitude of 2 or a star with apparent magnitude 7? By how much?
Class, which is going to be our A star? Which is going to be our B star in this case? Sorry, Caitlin. Remember, one of the screwy things about magnitudes is the lower the number, the brighter the star, right? And in our conception, since we're doing a ratio of A to B, we should put the big guy on top, okay? So that's what I was wondering. So we'll call magnitude A 2, and we'll call magnitude B 7. So the ratio of a magnitude 2 star to the ratio of a magnitude 7 is 100 to the power of what?
Would it
Would
be
be
7 minus 2 divided by 5?
Exactly.
Wouldn't that just be 1 though?
Exactly. Which is 100 times ratio and flux, because they are 5 magnitudes apart. So I want you to write above it, a magnitude 2 star is 100 times brighter than a magnitude 7 star. Get all that down before we continue, because I need to erase. Yeah, it's hot today. I really want to go outside after this. Okay. Here I go. Erasing. Today, I finished my lecture on apparent magnitude. Are you a tennis player, Arunsak?
I'll play a little bit.
It sounds fun. We're going to do something on absolute magnitude. Absolute magnitude uses the letter capital M, and it is a tracer of luminosity. I'll explain it better next time, but for now, the formula is the exact same as the brightness formula. The luminosity of star A to the luminosity of star B is 100 to the power of the change in absolute magnitude. Notice my use of capital M divided by 5. With that in mind, Christopher can read us part B.
Okay. Which has a greater luminosity, a star with absolute magnitude of -4, or a star with absolute magnitude of +6? By how much?
So Caitlin, which is the A luminosity star going to be? Oh, wait, sorry. It's not luminosity, it's absolute magnitude. Which is the A1 and which is the B1?
Are we still talking about the M2 and the M7 or something different now?
It's a new one. So it's new in 2 ways. Now it's 2 different stars, but it's a related quantity to apparent magnitude. It's called absolute magnitude, but it basically works the same way. So based on intuition of what you learned last time, if we have a star with absolute magnitude -4 and a star with absolute magnitude +6, which will be the more luminous star?
-4.
That's right. So we're going to call the A magnitude -4 and the B magnitude +6. So L -4 over L +6 is 100 to the power of 6 minus -4 divided by 5. 6 minus -4 is 6 plus 4. 100 to the power of 10 over 5, or 100 squared. What is 100 squared, students?
10,000.
Good. 10,000 times more luminous. So a absolute magnitude -4 star is 10,000 times more luminous than an absolute magnitude +6 star. And that wraps up our fourth problem. We are flying. I'm like an even worse version of a Rhode Islander. Most Rhode Islanders don't like to leave Rhode Island because it's too far. I'm like that, except for downtown Providence. If I have to leave downtown Providence, it's too far for me. I want to forget, like, not even in the city. I just won't leave downtown. This social distancing thing is kind of working for me in that respect. I don't have to go very far. This is our fourth problem down the hatch. And I'm going to, yeah, I remember when I went to college, Christopher, in Tucson, Arizona, people would be like, hey, do you want to go see a show up in Phoenix? And I was like, wait, how far away is Phoenix? Like, that's only 3.5 hours. I was like, are you crazy? That's insane. They would think nothing of just going to a show 3.5 hours away for like an evening trip. That was crazy. Okay, I'm going to erase. Yeah, I guess, see, if you live in these Midwestern states, or even the West where it's even more sparse, you're just like, car life is part of life. And it's very beautiful out there too. The drives are very mesmerizing. But as a native Rhode Islander, I can't fathom the idea of even driving for 15 minutes. You know what, Gianna? Be careful when you say that, because you can really grow to love a place once you discover what's special about it. When I first got to Tucson, Arizona, I thought it was the ugliest place on earth. I thought like the earth had thrown up its guts and it was just sand and brown and nature was mean and it wanted to kill you. And after 3 or 4 years of living there, I started to realize how beautiful and magical the desert is. So Rhode Island's got its own special magical things. Don't give up on it. Yeah, Rhode Island's very nice. Okay, I like it anyways. I'm passionate. I'm passionate about Rhode Island. Let me erase this. As I tell my New York friends, it's a small state with a high density of cool. That's my pitch. Aww. All right, so chapter 15, number 57. Our final problem is on a binary star system, and we're going to use NK3 for mass. All right. What's the title? Kaitlyn, did you ever get your thing together, or maybe we can have a run set? No, okay, that's all right. We'll let you off the hook.
I don't know why it won't do anything, but sorry.
Okay, that's okay. I just kind of like to get everyone to. Yes, Stacy, we do have a new date for the. Actually, I have.
That was to you guys.
Oh. So I have 2 gigs coming up now. That gig that got canceled because of rain is now on November 6th, and that's at dusk. But the one I'm really looking forward to is Friday, November 13th, and that's at this cool distillery called ISCO. And it's a distillery that makes their own homemade gin and vodka, and their stage is really, really beautiful. It's under a big hangar with these magical red and pink lights. And there's going to be a dumpling food truck there. No, a pierogi truck. That's what it is. It's going to be a pierogi truck. So I can eat pierogies before or after my set, which sounds great. It's a distillery, so I don't know. I don't know. I'm sorry. I forget that some of you guys are youngins, just little young tykes. But I'll find out from the people if it's all ages or not. Okay. Okay. Arunsak, can you read us a problem? Are you set up to do that in the coffee shop or? Okay. Stacy, it's back to you then. Okay. Thank you, Stacy.
That's fine. I don't mind. Extra credit here, right?
Yeah, absolutely. We'll
Yeah, remember
little
that.
something on the
Pluses suck. All right, 57, measuring stellar mass. The spectral lines of two stars in a particular eclipsing binary system shift back and forth with a period of 6 months. The lines of both stars shift by equal amounts, and the amount of the Doppler shift indicates that each star has an orbital speed of 80,000 minutes per second.
Wait, sorry, that's meters per second.
Meters per second, that's what I meant, sorry. What are the masses of the two stars?
Okay.
Assume that each of the two stars traces a circular orbit around the center of mass. And there's a hint if you want it. Nope, never mind.
What's the hint? Just
the hint is see Mathematical Insight 15.4, so probably not gonna help.
Let me explain what's up with binary stars. When we consider the orbits of binary stars, we're going to do a kind of thing where let me draw a circle here. We're going to imagine that one star is a little star, and it's basically orbiting around the big star like a planet, okay? So let's let the big star in the center be called M1. And let's let the little star orbiting around it be called M2. And because technically the orbits, because the orbits are ellipses, the center-to-center distance is called A for the semi-major axis of the orbit. But in this case, the semi-major axis A is the radius of orbit, okay? Now I want you guys to make an argument with me. You've heard of the formula distance equals rate times time. Probably at some point in your life, you had to do this in a high school class. Let's imagine one single orbit of the star all the way around the circle. The distance the star travels is the circumference of the star, which I'm just going to call CIR for circumference. The rate is the velocity of the star, which is a measurable thanks to the Doppler shift. Someone brought up the Doppler shift earlier today. I'll talk to you guys about the Doppler shift next class. What would the time be if I go all the way around the circle and travel the circumference? What can I substitute in for time?
Pi.
360 degrees.
Well, that's an angle. It certainly is 360 degrees. But if we express it as a time,
Six months.
yes, or we'll call, yes, it's the period. I'm temporarily going to call it P because I'm developing a formula, but 6 months, right? Okay, do you guys know the formula? You probably forgot your geometry. Do you know what the formula for the circumference of a circle is in terms of its radius? No?
Isn't it pi r squared?
That's the area of a disk. This is pi r
It's 2
squared.
pi r.
2 pi r. Remember that pi is the ratio of the circumference to the diameter. So the circumference here is 2 pi a because a is our radius. We want a because a is used in Newton's version of Kepler's third law. In Newton's version of Kepler's third law, the total mass of the system is basically like a cubed over p squared. We can solve for the a. This is a new formula called the binary star orbit formula. V times p over 2 times pi. You will need to use this on your final exam. So I'm trying to warn you about this stuff, okay? This is the binary star I don't have a better name for this, so I just call it the binary star formula. It's a way to go from a velocity to a distance. Okay, let's make sure we get our units straight. We've got meters per second in 6 months. I've tried to warn you guys before, maybe I warned the other class, months are a terrible unit to use because they're inconsistent. Luckily, 6 months is equal to half a year. So if the period is 0.5 years, do you guys remember the conversion from years to seconds?
I got you.
Yep.
It's 3.15 times 10 to the 7th.
Excellent. So it's 3.15 times 10 to the 7 seconds per 1 year. Half of 3 is 1.5. Half of 15 is 7.5. So 1 point, oh God, I'm bad at this. $1.575 times 10 to the 7. Is that right? Wait, did I screw that up?
I think it's like 1.6. 1.6 times 10 to the 7.
Fine. Seconds. Okay. Now we can put that into the binary star orbit formula. Okay, so we did that right, correct? Did we do that good? Okay. So A is equal to 80,000 meters per second times 1.6 times 10 to the 7 seconds divided by 2 pi. Let's punch that up. Ooh. I'm fading here. 80,000 times 1.6 to the 7 divided by 2 divided by pi. What you got?
To the 2 times 10 to the 11.
Units?
Meters per second squared.
No, this is meters per second. This is the top of the top, and this is the bottom of the top, right? Meters, says Blair. It's a distance. Okay, that is only half of our answer. We needed to do this to get the A because our goal is to find the masses, and we need to use NK3 up here to do that. We have the period, we now have the A, we can solve for the masses of the 2 stars. So we want NK3 for mass. M1 plus M2 is 4 times pi over G . 7 times 10 to the minus 11 meters cubed per kilogram per second squared. Woo, times A cubed over the period in seconds squared. Now you guys had a lot of trouble with this on the test. Let's see who can do it and who can't. But I hope you're all practicing. By the way, I meant to do a little experiment with grades. I wanted to see if the people who share their video with me scored on average higher than the people who don't. but I haven't done that. I want to try that average over many people. There were some extraordinarily high grades on the exam, by the way. They were all over the damn place, but not many, but a few. Oh, did you guys notice I'm missing something? The highest score was a 97. Someone got only 3 points wrong. And they were in the night class too. So it was like, whew, that was amazing. Did you guys notice? You probably didn't. I forgot the square on my pie. Hey man, nerd is the word. You know what I'm saying? I love that song, by the way. Indeed. Do you guys know how to do this, or do I need to do it with you? It'd be cool if you knew how to do it.
It's just long.
I got it done.
You're the professional, though, so
That's true.
you should.
You can be just as, come on, you guys are young and full of beans. You can do this. True. Okay, fine. Right. Sorry, Kevin. Too low. You forgot your cube or something. Anyone? Kaitlyn, are you zoned out, or do you have an answer? Are you punching? Come on, what are you doing here? You're punching? Emily, what about you, buddy? Someone talk to me. I'm so lonely over here.
Is it 1.76 times 10 to the 31st kilograms?
Excellent. Who was that?
Kevin.
Oh, nicely done, Kevin. I think we better do that with the class. Do you want it slow or do you want it fast? Slow? Okay. 4 times pi squared times 2 exp 11 shift cube. Now I'll divide by g, divided by 7 exp negative 11. Now I'll divide by p squared, divided by 1.6 exp7. Then you've got to square that, and then you hit equals. 1.8 times 10 to the 31 kilograms, says Kevin. Let's convert that to solar mass units. What's the conversion to solar mass units? It was in your notes today.
2 times 10 to the 30th kg for, and 1 on the top.
Excellent. Okay. So that gives us 8.8 solar mass units. Now, they wanted the mass of each star, and I'm not going to try to explain it all to you now, but I'll say this. The equal Doppler shifts means equal velocities. The two stars have the same velocity ratio, and that implies that the two stars have equal masses. That's a concept from studying binary stars that I'll have to tell you about later. The ratio of the velocities is the inverse ratio of the masses. So each star has half of that. Is 4.4 solar masses. And we'll just call that a freebie. And with that, homework number 7 is completed, and it's only 2:30. So we did awesome today. 12:30, 2:30. 3 hours. That's our record time for us. I agree. Okay. Now, students, I really want to impress on you, night students, background students, Austin in particular, that we are going to get these homeworks in a very timely fashion so that I can grade them on Sunday, right? The lesson that I gave you at the beginning of class today was that keeping those homeworks and labs high is the key to success in this course. So thank you, Gianna and Kaitlyn and all the other people photographing right now. Just get it in and then let's be done with it, okay? Okay. If there are no other questions, I will stop the recording, which I will do now.